Welcome to Chapter 5 for our trek through solar system astronomy. In your textbook, it's going to talk about light, properties of light, and how we can see different kinds of things. In Chapter 6, we'll look at telescopes and look at the particular ways in which we can look at what we're seeing here. This image will hopefully become a little more clear to you, the image I have behind me here, as we go through the lecture, so stay tuned. And if you're watching this video anywhere near the time that I'm actually recording it, happy solstice, happy summer solstice. If not, then happy whatever day it is you're watching. But I am recording this on the summer solstice, which of course here in Indiana means we have clouds, but that's the way it goes. Let me see if I can figure out how to share the screen. I think, is it that one? Yes. When we're talking about light, we are talking about radiation. And when we're talking about information from the light, we're talking about spectra, spectral analysis, those kinds of things. So we're going to play from start here. And one of the things you might notice is that sometimes I'm using slideshows from a different textbook, but in fact, what happens is a lot of textbooks are structured in a very similar way. So Chapter 5 in a couple of different books that I use are all about light. So the information that I'm going to give you here is the same whether you're using Cosmic Perspective or the OpenStax astronomy book or any number of other textbooks along the way. So the information that I'm giving you will be relevant, although it may not be completely organized exactly in the same stair-step way as the book that you're reading. So pay attention to that. We may jump around a little bit compared with what you're reading. So when we're looking at light, we are seeing things that are entering our eyes in particular ways and are activating our sense of sight in a particular way. We cannot see all the different types of light that are out there. We see Roy G. Biv, which is the sort of the backdrop that I have here. We cannot see in infrared. We cannot see in ultraviolet. We cannot see in X-rays. We cannot see in gamma rays. Sometimes I ask the question, how many of you have ever seen an X-ray? And everyone raises their hand. It's like, nope, sorry. What you're seeing is the aftermath after X-rays have gone through, but what you're seeing is the Roy G. Biv of what's left over when the X-rays go through. We can't see X-rays. They're invisible to us. We can't see radio waves. They're invisible to us. Ultraviolet is invisible to us as well. The sun actually puts out things in ultraviolet and infrared and radio waves and even X-rays. So we do get some things off of the sun. Most of the energy from the sun comes off in Roy G. Biv, which is what our eyes have attuned to, what our planet has evolved to respond to. It actually responds mostly to Roy G. Biv, the visual light spectrum. But if we look at the sun or other objects in our solar system or even beyond with an ultraviolet sensor or with an infrared sensor, we can actually see that these things are still luminous in those wavelengths. And we'll talk about those different kinds of things as we're looking along. So that picture is of the sun, but in ultraviolet, which means if we were looking at the spectrum behind me, it would be down below this blue level. That would be beyond the violet, ultraviolet. When we're talking about light, we're also talking about gamma rays, X-rays, ultraviolet, infrared, radio waves, microwaves. We're really talking about what we call the electromagnetic spectrum. And we have this guy to thank. You may have heard of Maxwell, James Clerk Maxwell. And he is the person who really figured out that light and magnetism are pretty much the same thing. They are a sort of a combined force. We used to think of electricity over here and magnetism over here as separate forces, but when he was doing the math behind it, and don't worry, I'm not going to make you do the math behind it, but as he was doing the math behind it, he said, these equations here look a lot like these equations here. Hey, my goodness, look at that. And so now we talk about the electromagnetic spectrum, thanks to his work, as you can see in the middle of the 1800s, which in terms of human history is not that long ago. Before this time, and even during this time, there was a controversy of whether or not light was particles, little bits and pieces, or if it was waves. And there were different schools of thought about it. Isaac Newton thought it was particles, and he called those particles corpuscles. And calling those corpuscles becomes a little bit of a problem because corpuscles are what flow through your bloodstream. They're actually something else. So now we call them photons. There were others, sort of a contemporary, late contemporary of his, named Huygens, Christian Huygens, who thought of things as a wave. And it went back and forth. Is it a wave? Is it a particle? Is it a wave? Is it a particle? For hundreds of years until we sort of figured out, hey, it's actually both. But we'll talk about it in terms of both waves and photons, in terms of particles. When we're talking about waves, we're just talking about waves. Like you see here in the pond with our frog, our friendly frog, making waves. They go out. Notice that they spread out as they go out further and further and further into the pond. They're going to be the most intense around the frog here. They're going to be the least intense as you get further and further out along the way. Waves are fairly easy to describe. We go from top to top. Those are called the crest, or trough to trough. Those are called the bottoms. What we have here is a wavelength from crest to crest, or from trough to trough, top to top, bottom to bottom. We could also measure a wavelength by the midpoint, but you'd have to take 3. Why might that sometimes be preferable? Well, if you get your waves cut off, if they're going through something and you get some cutoff there, and that can produce all sorts of interesting quantum effects, and we may talk about that later in our semester. But the wavelength is something that you can just measure. You can take out your ruler and measure it. Although the light that we're seeing behind me here, the light that hits our eyes, are very tiny. In fact, when I put my fingers together, you could still get a light wave between those two. On the other hand, radio waves, one radio wave could actually stretch out for 1 football field or longer along the way. But the thing is, they all go at the same speed, the speed of light. The speed of light is, in fact, the frequency, how many of them you have, multiplied by the wavelength. And see, we have our little lambda here, and we have our frequency with an F. Multiply those together, it gets C. That's the speed of light. We use a lowercase c as the speed of light, which means if one of these goes up, the other goes down to keep that relationship going. We also have amplitude, which is the size of the wave. We won't worry too much about that for our purposes here, but you may be aware of amplitude when you have a car, especially if you have an older car that only has an AM radio, that amplitude modulation. You get radio signals by varying the size of the wave. Frequency modulation varies this along the way. As we look at things, we can see an electric field and a magnetic field overlap. Thank you, James Clerk Maxwell. And what we have with light is oscillating fields. Don't worry too much about the physics that are involved with that, but just be sort of aware of that. As they're traveling along at the speed of light, which is c. I think we've covered that a little bit before. 300,000 kilometers per second, 186,000 miles per second, or we could say 3.0 or 2.99, we're rounding up usually to 3, times 10 to the 8th meters per second along the way. So when we're looking at our whole enlightenment here, we call it the electromagnetic spectrum. Here's what we see, visible light, Roy G. Biv. Notice Roy G. Biv right in the middle there. Notice that as we get past the Biv, we go beyond the violet, we've got ultraviolet. Notice the waves are getting shorter and shorter and shorter. We get ultraviolet, then we get X-rays, then we get gamma rays. These get more and more and more deadly, more and more powerful. If you're hit by radio waves, doesn't matter. If you're hit by X-rays, yeah, that's going to matter. When we're looking back here, we're beyond the red, we're infrared. So these waves, if an X-ray hits you, even just one, it has the potential for doing damage. If radio waves go through you all day long, because they are, in fact, as you're sitting there right now, radio waves are going through your body. And the reason why I can tell you that is go turn on your radio. and you can go to one station, then another station, then another station. They're all in the air. Doesn't matter, doesn't bother you at all. The reason why microwaves, you don't want to get into the microwave and use that as a substitute for tanning booth, is not because any individual microwave would be a problem, but they're intensified in the environment of your oven, so you don't want to do that. Just like infrared, any given infrared ray isn't going to hurt you, but intensified, it can heat up. So these don't need to be intensified too much because they're already intense just by themselves along the way. But we can see lots of things out in space based on what it is we're looking at here. Black holes show up usually fairly well in X-rays. It's not the black hole itself, though, that's showing up. It's the stuff around it that's showing up. Stars show up in visible light, also in ultraviolet and infrared. When we're looking at things that aren't putting out their own light in Roy G. Biv, typically we're looking at things that are lower energy. These are lower energy over here, or things that are enormously far away, radio galaxies, for example. So when we're looking at our own light, we've got red light to blue light, sort of red to blue, sort of top up here, down to the bottom. Here, the top red is going to be longer waves, then it gets shorter and shorter and shorter and shorter all the way down to blue. Notice we go from about 700 nanometers to 450 nanometers. So in other words, blue light is getting close to, by the time we're into violet, pretty close to half of what the longest of the red light will be. We can't see with our eyes, just naturally, anything that is longer than the red, that's what gets into infrared, or anything shorter than the blue, which gets into ultraviolet along the way. So when we're looking at ultraviolet, they can go all the way down to 10 or so. By the time we get up to radio waves, we can get to a meter, or even, as I mentioned before, you can get a football field long wave that's coming at you there. When we're looking at these things, we look through the atmosphere. The atmosphere does interfere with quite a lot of stuff. It doesn't tend to interfere too much with radio waves, standard radio waves. That's why radio transmission works fairly well. You can get static electricity, you can get thunderbolts and other kinds of things like that, and that'll interfere. But just the regular old atmosphere doesn't tend to interfere with things. So if it comes from outer space to our radio dishes, we get a perfectly good signal. It does interfere a little bit with Roy G. Biv, and it does interfere a little bit on the edges of Roy G. Biv with ultraviolet and with infrared. That's why we tend to put our better telescopes on the tops of mountains so that we can eliminate part of the atmosphere as we're doing it. But the atmosphere, as you can see here, blocks quite a bit of infrared, blocks even more of ultraviolet, tends to block the X-rays and gamma rays as well, which is good for us because if it didn't, it would sort of just eliminate all life on Earth with these kinds of things here. So if we're looking for X-rays, if we're looking for gamma rays, if we're looking for certain levels of infrared, we can actually go up in planes to see it when we get above enough of the atmosphere. But putting things up above the atmosphere entirely eliminates this issue, including Roy G. Biv. That's why we have the Hubble up there. And we'll talk more about that in our next chapter. Here again, you can see radio waves make it all the way down, except for the ultra long radio waves. They will once again often tend to be blocked. And it's not exactly being blocked, it's that they're sometimes too long to catch. Infrared has pockets of areas that come through. Visible light, as you can see, doesn't make it all the way down unobscured. What we're seeing, twinkle, twinkle, little star. That's not the star twinkling. That's the light coming through the atmosphere that's causing the twinkle over there. And again, fortunately for us, most ultraviolet X-rays and gamma rays are completely blocked from us. So when we're talking about looking at those things, we either have to use really special equipment, adaptive optics, or we have to get above the atmosphere. We didn't know how energetic the universe was in terms of X-rays until we got some things up above our atmosphere and we began to see things. This was from a European, an ESA satellite, the ROSAT satellite. We also have a NASA satellite in X-rays observation called the Chandra. We'll see again more of that when we get to chapter 6. But when we look at the universe in X-rays, what we're doing is we're transposing the light from X-rays down to Roy G. Biv so that we could see it. Otherwise, we wouldn't be able to see it. It would all be invisible to us. But we can see there's some high energy levels and some low energy levels. And we can see that there's a couple of bright spots that are there. Often those correspond to very active areas. When we're looking at light coming at us, we can break it into its constituent parts. If you have a prism, which is often something you can buy for relatively low prices on Amazon or from teacher and school shops, homeschooler shops will often sell these. You put the light through it and it breaks it into a rainbow. This can happen in some natural ways as well. But what we get is a spectrum. We get Roy G. Biv here. Here it's sort of backwards from, so we've got the Vib G. Roy G. Biv in this way. So your eye sees these areas here, doesn't see this stuff. This becomes invisible, doesn't see this stuff. This becomes invisible along the way. So it's dispersed, and this would be called a continuous spectrum. If you have light coming directly off of the sun, if you have light coming off of like an incandescent bulb, you're pretty much going to get a continuous spectrum that's here. What's happening as the light goes through the prism is we have some longer rays and we have some shorter rays. The shorter rays, as you remember, are you have that wavelength and frequency kind of relationship here. When you have a longer wave, you have a lower frequency. When you have a shorter wave, you have a higher frequency. So that's sort of what's happening here as it comes through. And they're going through this, they're each looking for, each area of light is looking for the path of least resistance and the fastest course through. And prisms will naturally change that for us. When we're looking at heat signatures, there are different mathematical ways of presenting this, but one of the ways in which that often happens is we have this here. We have what's called the Stefan-Boltzmann law, and we have what's called Wien's law here. And this one's referencing Wien's law here. What happens is the hotter and hotter and hotter things get, the more and more up they go towards the ultraviolet and perhaps even into the X-ray area. But we're talking about planets and stars here, so we're only going to talk about going up into the ultraviolet, really, on this level. If it's a cooler thing, it's going to peak over here. If it's a hotter thing, it's going to peak in the ultraviolet over here. If most of its light comes off of ultraviolet, if its peak intensity is over here, the closest thing we can see is still going to be in the visible area, so it would look bluish to us. If it peaks over here in the infrared, then the closest thing we'll see to the peak is going to be over here on the reddish side. So if stars look reddish, they're cooler. If stars look bluish or purplish even, they're going to be hotter. So our sun puts out the most light right in the middle of Roy G. Biv. So we're right at the yellow, the Roy, edging towards the G side of Roy G. Biv along the way. Everything puts out heat unless it's at absolute zero. So your body is putting out heat right now too, but it's putting out light and heat in the infrared area. That's why you can't see, if you turn off the lights, you can't see yourself in the dark. But if you get infrared goggles, what that does again is it takes the light and shifts it to what we can see, because it can pick up the heat signature, which is actually the infrared light signature that's happening there along the way. So this stuff is mathematically calculable. We can sort of figure these things out. The brightest colors will be from due to the intensity where it is most intense. Again, if it's ultraviolet, it's going to be over here. The color is going to end up being on the blue side. If it's most intense is over in here, the color is going to be on the red side. The total amount of energy coming off of anything is based on this Stefan-Boltzmann law here. But for our purposes in this class, you're not going to have to know too much about it, but just be aware of what's happening there. And here is an explanation of what is behind me here, although it's upside down from what I have up here. Remember, not all pictures north is up. You can do different orientations along the way. These dark lines are part of what's telling us what's inside the sun in terms of its elements, its chemical construct, what is made up of the sun, or what the sun is made up of in terms of hydrogen and helium and calcium and other kinds of things. When we're looking at the light coming off of the sun, we can get a continuous spectrum, but we can also use various adaptations to get what are called spectral lines. Hydrogen, as you see, has 4 particular lines here, and it's the most common element in the universe. We also have sodium. Notice it's got some particular lines here. Calcium has particular lines. Mercury has particular lines. But there are 92 naturally occurring elements. Each of them has a unique fingerprint or signature like this. Hydrogen is the only element that puts out these 4. Now, you might have some overlaps, like this one with calcium here, this line here, but that is what you then do as you analyze a chart like I have behind me here and figure out which one is which, because you're going to be able to match them up. Prisms and refraction to get a continuous spectrum happen in nature. Just like a prism, if you look at little c here, our graphic for c, you can see the sunlight coming into the water droplet and bouncing around before it comes out as a rainbow. Rainbows are sort of angle specific. So if you're looking from over here rather than from over here, you may not see the rainbow, or you may see a partial rainbow, or you might see a faded rainbow. Whereas if I'm looking this way, I'll see a great rainbow, and over here I might just see the fuzzy outline of one. Because the same is true when you're holding a prism. Try that sometime if you can get hold of a prism, and it won't make the same image. It won't break the light apart in the different angles. You have to angle it right. This is called refraction. But there are different things that will do this. Water does that. Oil does that a lot. As light comes off of anything, it loses its intensity. We've talked about this before, the inverse square law for light. As you get twice as far away, you only have 1/4 of the intensity. As it gets 3 times as far away, you only have 1/9 the intensity. The waves spread out, just like the waves from around our frog earlier. As it spread out from the frog, it got less and less intense along the way. But as light hits things, sometimes it can go through things. Glass window, that's something that's actually physically there, but things come through. Sometimes you'll have plastic, it'll come through. Some things won't let it through. So some things will block the light entirely. Some things will let light through intermittently. Some things will let light through all the way. What's happening here? Why does this happen? Why does light sometimes bounce back? Why is light sometimes absorbed? These ideas come from experiments that were started by a guy named Ernest Rutherford. And Ernst Rutherford figured out from this the interior of our material, our matter. The most abundant element, as I mentioned before, in our universe is hydrogen. So hydrogen is also the simplest. It has 1 proton and 1 electron. Typically, there's some little variation I'll talk to you about in just a moment. This is massively, massively, massively not to scale. If you've been thinking about the lab where you sort of had to have the sun and then the planets and then they got further and further and further out. If this were the size of a proton, the electron would be orbiting out by the moon. There would be that much empty space inside an atom. That's why if a photon is coming along, hey, it might miss things entirely. So it doesn't just depend upon the individual atom, though. It also depends upon how they're connected to each other in molecular scales. But this is a typical atom. We have an electron has a negative charge, a proton has a positive charge. Sometimes in the middle, you'll also have extra particles called neutrons. They're neutral. In a typical atom, you're going to have the same number of electrons that you'll have for protons. So here's helium. It's element number 2. Hydrogen is 1. It has 2 protons. Notice it also has 2 neutrons, but we give it its atomic number based on the number of protons that are in there. And it will have 2 electrons, so it balances out along the way. Again, if this were the nucleus, this is the center of the atom here, the electrons will be out probably a couple 100,000 miles away, like out by the moon. There will be, again, that much empty space that's in there. As I mentioned before, you can get a couple of variations. This is hydrogen. Guess what? This is also hydrogen. Guess what? This is also hydrogen. Why? Because hydrogen has 1 proton in the center and typically 1 electron up here. When I say typically, it's because the electron can disappear and come back. But we still talk about this as being helium. When you've got a neutron, that does not affect whether or not this changes from hydrogen to something else. Carbon is also something that happens there. You may have heard of carbon-14 dating. Carbon typically has 6 protons and 6 neutrons, but sometimes it has 7 and sometimes it has 8 neutrons. Still carbon, but if it's carbon with 7 neutrons, it's carbon-13. If it's carbon with 8 neutrons, it's carbon-14. Well, those aren't all that stable. These typically also can be less stable than this. Which, I mean, how can you get any more stable than 1 here? But these will sometimes disappear. They will sort of decay. We call it decay. And carbon-14 decays over time. And if you can tell how much decay has happened, you can tell how old something is. Carbon-14 dating along the way. These variations are called isotopes. So they are isotopes. Some of the guys who helped us figure out what's in the middle of the matter that makes up the entire universe are Niels Bohr and Max Planck. Niels Bohr is one of my favorite characters in 20th century science, early 20th century science. In Copenhagen, in Denmark, people were so impressed with his scientific ability that there was a brewery that was built near his house, and they put a line in so he could have beer on tap from the brewery, sort of in appreciation for his scientific ability. But one of the things that they figured out was inside here, you don't just have an electron going around. This is actually a 3-dimensional thing, so think about it more like a sphere that moves in different ways. But the electron doesn't go all the way out and all the way back in. It jumps from one spot to the next spot to the next spot and then jumps back. So it only goes around in certain places. It doesn't just willy-nilly go everywhere along the way. And the way we sort of figure that out is as things are coming into the atom, if it hits the electron, it goes to a higher orbit or a higher shell. If it loses that energy, if it loses that photon, it drops down to a lower energy state, but it always goes from one to the next. And those are what these lines all correspond to. And there are different series that are in there. Some of them absorb. So as it's absorbing, or if it's emitting things, then it's going to either jump to a higher state because it's absorbed energy, or it's going to drop to a lower state when it's emitted things. Don't worry so much about Balmer and Lyman and Paschen here. Just be aware that this is how it works. This is how it works inside. So all of these lines that we're seeing, whether we're getting the lines because it's absorbing the photons or lines because it's emitting the photons, these all correspond to those jumps. And each element has a different sequence of those shells that give us the different lines that are out there. So we get what are called continuous spectrum when we don't see the lines. We get the bright line or emission spectrum when we're looking at the light coming off of something that is giving us the emission of those. Or if we're looking at, say, a light behind something that's absorbing part of it before it gets to us, we're going to get an absorption spectrum. So absorption spectrum here we have absorption. Emission spectrum here, we have the word emission down here, and continuous spectrum when we're not seeing any of those at all. These are related to the Doppler effect in the same way that sound waves are related to the Doppler effect, or influenced, can be described by the Doppler effect, I suppose I should say more precisely. If you are listening to a police car or a fire engine or an ambulance and it's just sort of sitting there with the siren on, it's at a certain pitch. If it is coming towards you, if you're driving along and you hear a siren behind you, it usually sounds at a higher pitch than when you pull over and let the fire truck go by. The pitch of the siren seems to go down. Well, as the waves are coming out of the siren, if it's coming towards you, it's actually driving into the sound waves that are already there, and it's pushing up. It's adding energy to them. It's blue shifting things, because again, blue is higher energy. So it sounds like higher pitch. When it's going past you, there are already waves in the air, but it's putting out more waves. They're acting sort of like baffles, and it's lowering the energy, it's lowering the pitch. So that's why it goes from high to low as it goes past you. That happens in sound waves. That also happens in light. If we're looking at these spectral lines here at rest, say these are the lines of our element here, if it's coming towards us, again, the waves are coming into the waves already emitted, and it'll be pushing them up. So we get a blue shift. Notice that all of these things, all of these lines are closer to the blue. If it's going away from us, we get that baffling effect. So notice all of them are shifted more towards the red that's there. So red shift is away from us, blue shift is towards us. And we can use this kind of information in a lot of different ways, because we can see if something's red shifted, if it is going away from us. We can even sometimes tell how fast it's going away from us by looking at how much of a shift has taken place. Or if it's coming towards us, how fast it's coming towards us by the shift that's taking place along the way. But not always are we going to get the special case where it's coming directly towards us or directly away. So we have ways of figuring out, even at angles, what's happening there. Again, I'm not going to expect you to do all of the math and everything with regard to that. But be aware that that happens. There's one more thing I want to show you. So I'm going to pause for a moment and find the screen. Okay, I'm back. I want to show you, I want to share with you one more screen. So let me see if I can figure out where it is. I want to show you this screen here. So play from current slide. This is from a different chapter. But one of the things that this one shows is this element here, helium. Remember, hydrogen is the one with 1 proton. Helium is the one with 2 protons, has also 2 neutrons, so it has 4 particles in the center there. But when we're looking at these, we're really paying attention more to the electrons than the nuclei, the protons and neutrons. No, I want you to notice something here. See our hydrogen lines? We've got 4 hydrogen lines. Notice sodium, NaCl, like that's something you have in your house. Sodium is part of salt, so we have to watch our sodium content coming in. It has this 1 line here. Notice what's happening here with helium. We've got 3 lines that look a lot like hydrogen. We've got this line that also that looks like hydrogen. We've got this line that looks like sodium. We've got this weird extra line over here off in the red. When people were looking for this kind of signature from starlight, in particular the sun, we found these lines coming off of it. And at first it seemed like, well, these might be hydrogen and sodium lines combined. There might be a lot of hydrogen and sodium in there, but we kept getting thrown off. The researchers, I'll include myself among them, even though I wasn't there. we as investigative species kept getting thrown off by this extra line over here. Because helium, until we discovered it on the sun, had never been discovered on Earth. Now, you've probably used helium at different times in your life, probably in balloons. How many of you have ever taken a balloon of helium and sucked it up? Okay, well, what does it taste like? You probably don't remember. If it tasted like anything, it probably tasted like the balloon, because helium itself doesn't taste like anything. It doesn't smell like anything either. It also isn't flammable. You can't like take a thing of helium and then set your lighter to it and have it go, because it doesn't do that. So there was really not a lot of ways to figure out where helium was on our planet if you didn't know it was already there. If you found this cavern full of helium and you opened the cavern, what would happen to the helium? It would all escape. So this was something that was actually discovered thanks to these spectral lines on the sun before it was discovered on the Earth. And that's why it's called helium, because the Greek word for sun and star stuff is helios. And therefore we get helium as star stuff. And it was discovered on Earth after it was discovered there. So I just wanted to share that. That comes from a later chapter, but I wanted to share that with you because it's a neat little piece of how we can sometimes find things out there before we found them here. What difference does astronomy make? What difference does science looking at other planets and stars and other things make? Well, guess what? We discovered helium. We hadn't discovered that before. That's actually a pretty big thing to discover. Helium is in fact a useful product for many industrial uses as well. So far beyond just balloons. Again, I thank you for paying attention this time, and I will be back and we will talk about telescopes in chapter 6.